Speaker this morning, Pierre le Boudec, whose talk is the second part of talk about the conjecture of Poonen and Voloch, lattice point counting and the variance of number of rational points on Fano hypersurfaces.
Thank you. So thank you very much to the organizers for the invitation, and thank you very much for the introduction. So my goal is to answer a question which was asked at the end of the talk: why n at least d plus 2? So let's see. So let me start by reviewing what Will did. So first, he showed that in proposition 1, he stated a result saying that it's a rare event that the localized counting function approximates poorly the global counting function. And in the second proposition, he showed that it's a rare event for locally soluble, ever locally soluble hypersurfaces, that the localized counting function is small. So if you put these two things together, it's a rare event for everywhere locally soluble hypersurfaces that the global counting function is small. But it's either 0 or at least 1. So if it's rare that it's far away from 0, then it's at least 1. So there's a rational point of height at most b. So in particular, there's a rational point. So that's the strategy. And Will has taken care of the second proposition. So now I'm going to focus on the first one. And as you may have noticed, in proposition 2, he didn't need any restriction on n and d. What he said works for any d at least 2 and n at least 3, I guess. Okay, so it has nothing to do with the Fano assumption. Okay, so my goal is to understand why we need n at least d plus 2, and maybe also why our method will not work for n equals d, which is the boundary case, so the hardest case. Okay, so let me start by stating again a version of proposition 1, which is going to be a tiny bit different from what Will stated, but morally it's going to be the same. So it's a non-completely explicit version. And by the end of the talk, we will have a completely accurate statement for proposition 1. Okay, so that's the goal. So there's a choice of parameters, so alpha, w, and b as functions of a, such that, so if we look at the ratio of the cardinality of the set of V in our parameter space, VDN of A, such that the global counting function is far away from the localized counting function, B alpha W is at least eta times B over A, then that cardinality divided by the cardinality of the total parameter space is, so let's see, I'm taking the lim sup as A goes to infinity. So I have not said anything about eta so far. So I have alpha, W, and B, which are functions of A. A goes to infinity. And I want that thing, that ratio, which now depends only on eta after taking the lim sup. I want it to go to 0 as eta goes to 0. Okay, so I guess that was one of your questions, the way propositions 1 and 2 were stated. So for the purpose of my talk, I'm doing exactly this. So alpha, w, and b are functions of a tends to infinity. So that now depends only on eta, and I want it to be small when eta gets to 0. Okay? So here is the idea. So when people who are used to counting see that kind of lower bound like this, they think second moment. So let's see why. So idea, method. Use a variance estimate. So I'm going to state a proposition 3, which is going to be also non-explicit. And I'm going to prove that proposition 1 follows from what I'm going to state for the variance. So similarly, there's a choice of alpha, w, and b as functions of a such that if we look at the sum over v in VDN of a of the second moment of the global counting function minus the localized counting function. So I square this, and I divide by the number of v in VDN of a. Then, so as Will said, we expect both NV of B and NV of B alpha W to be about B over A on average. So if there was no cancellation at all in that sum, then this would be about B squared over A squared. Okay, but I want it to be a bit smaller, so I'm going to put some power of eta here. Okay, and I should say that eta is some small parameter, between 0 and 1, say. Okay, and now I'm going to show that if we have this, then we get that. Okay, so proof that proposition 3 implies proposition 1. Yes, I'm gonna, so that thing, I'm gonna define it as V of A, B, alpha, W. And probably that ratio, I'm gonna give it a name also. I'm gonna call it P of A, B, eta, say. Okay, so we start with P of A, B, and eta. So we are counting the number of hypersurfaces V such that some quantity, so if I divide by the right-hand side, such that some quantity is larger than 1. Okay, so in particular, if I sum over V in VDN of A, that quantity squared, so in V of B minus NV B alpha W divided by eta B over A. If I square this, then either V is in the set we want to count, and that thing is larger than 1. So I'm summing something which is larger than 1, or V is not in that set, and then I'm summing something which is non-negative. Okay, so we have this inequality if I divide by the cardinality of VD and FA. Okay, so that's a classical trick in analytic number theory. Okay, now what do we get here? We get exactly, so let me remove the denominator. Let me take it outside of the sum. So we get 1 over eta b over a squared times 1 over the cardinality of the total space times the sum of the differences of between the global counting function and the localized counting function squared. So that's exactly the variance. V of a b alpha w. Okay, but now if we have proposition 3, then this is bounded by b squared over a squared times eta cubed. So by proposition 3, we get, so b squared and, b squared over a squared simplifies with this one, and we have eta cubed and eta squared below, so we get just eta. Okay? And that's good enough for us, because now if eta goes to 0, then that goes to 0, which is exactly what we wanted to prove. Okay? Oh, I'm taking the lim sup, I didn't write it, sorry. So here I'm taking the lim sup over A of P of A B eta. Okay, so that's by proposition 3. Okay, any question on that simple enough proof? Okay, so now we have reduced everything to an estimate about the variance of the global counting function. Okay, so the next step is to attack that thing. So let's see. So we're gonna sketch a proof of an explicit version of proposition 3. Okay, and I should say that analytic number theorists will recognize what we do as the dispersion method. So what is the dispersion method? So we are going to expand the square, and then we're going to end up with 3 different terms. So the sum of the global counting function squared, there's a -2, the sum of the global counting function times the localized one, plus the sum of the square of the localized counting function. And the dispersion method, what is it? So the principle is that if we are able to prove an asymptotic formula for each of these 3 terms, and so if everything goes well, then the main terms of these asymptotic formulas, they should be the same. And since we have 1, -2, plus 1, then they should cancel, and we should end up with something which is small, good enough for us. Okay, so that's the idea. Prove asymptotic formulas for the 3 terms. So the sum of a v of nv of b squared then the sum over v of nv of b and v of b alpha w, and the sum over v of n v of b alpha w squared. Okay, and here we have minus 2. And as I was saying, if the main terms are equal, which it should be, then since we have 1 minus 2 plus 1, then they're going to cancel. And we're going to end up with something which is small. Okay, so let's start with this first term. So it's the pure global term, if I may say this. So let's see. So okay, what is it? So the sum over v in vdn of a of v of b squared. So it's the sum. So when I sum over v in vdn of a, I'm actually summing over some polynomials fv in some power of z, and I want them to be primitive, and the sum of fv, the norm, sorry, of fv is at most a. And what is nv of b? So it's the number of rational points of bounded height on v. So I can write it explicitly as the sum over x in z to the n plus 1 with a primitivity condition. And the norm of x is at most b to the 1 over n plus 1 minus d. And there's a square here. So actually there's also a sum over y, like that. And I want, of course, a v of x to vanish and a v of y to vanish, because x and y are rational points on v. Okay, and so you didn't introduce that thing, I guess. So MDN. So it's the number of monomials of degree d in n plus 1 variables. So I think it's n plus d choose d. Okay? And prim means primitive vectors. Okay, so now what do we do when we have something like that? So we are summing over coefficients which have degree 1. And here we have conditions where the degree of x and y is equal to d. So we are not able to handle conditions of degree d, but if we switch summations, then dealing with conditions which are linear is of course much easier. Okay, so we're going to switch the summations. Okay, so if I continue, the sum of NV of B squared is the sum over x and y in z to the n plus 1 primitive, whose norms are at most b to the 1 over n plus 1 minus d. And then I have a sum over fv, whose norm is at most a, and such that v of x equals v of y equals 0. 7, 1. Okay, so now, so people who are used to doing this know that there's two cases here. So if x and y are collinear, then there's only one condition here, actually. Okay? So so fv of x equals 0 is one linear condition over on fv, and fv of y equals 0 is supposed to be another linear condition over fv. But if x and y are collinear, then there's actually only one condition. Okay? So that term, we're going to put it outside. And here I'm going to add the condition that x is not equal to plus or minus y. Okay? Both vectors are primitive, though, so they are collinear if and only if we have x equals plus or minus 1, plus or minus y. Okay, and here we end up with, so let's see, so if x is equal to y, there's only one condition. And then we recognize simply the sum over nv of b with power 1 here. v over b dn of a. Okay, and I guess I realized that there is some coefficient here, 1 over 8, because I could have chosen minus x, minus y, and minus fv. Here also, and here it goes away. Okay, so what is this? The sum over fv is simply a sum over coefficients which satisfy two linear conditions. Okay, so we are actually counting points in the lattice, which I'm going to call lambda xy, which is a set of a v in z to the n such that a v of x equals a v of y equals 0. Okay? And as I said at the beginning, we are not able to deal with counting rational points when we have something of degree d for any d, but now it's linear, so it's very easy, right? Well, at least it's easier. Okay, so then what? So what are we doing explicitly? Yes, so let me try to be a bit more explicit. So I'm going to call let a0, a1, a2, etc. in z to the n be the coefficients of the form fv. So I'm going to try to show you what we get if we use the most stupid way to count possible. And I'm going to try to explain how we can improve upon this. Okay, so yeah, and we are using the lexicographical ordering of monomials. Okay, so explicitly, we are dealing with something which looks like this exactly. So a0 x naught to the d plus a1 x naught to the d minus 1 x1 plus a2 x naught to the d minus 1 x2 plus, and then there's all the remaining coefficients equals 0. And same here with y0, y1, and y2. So a0, y0 to the d plus a1, y0 to the d minus 1, y1, plus a2, y0 to the d minus 1, y2, plus, etc. equals 0. Okay. here is this. So I'm going to keep that for later. Okay, so what happens if we count in the most stupid way possible, in the worst possible way? Then, if we look at the 2x2 minors of these two equations, then we see that, so counting in an elementary way, we see that what we need is that the size of the coefficients, so A0, A1, A2, we need it to be at least the size of the 2x2 minors, which is about x norm to the d times y norm to the d, and there's a, sorry, d over n plus 1 minus d, and d over n plus 1 minus d. No, sorry, yeah, it's fine. Thanks. D. Okay, so, which is the same as a at least b to the 2d over n plus 1 minus d. Yeah, thanks. Which is not so good. Because if we use that condition, then we're going to end up in the end with something like n minus d is at least 2d. Okay, so we would lose many cases. In the end, we want just n minus d at least 2. Okay, so here is an idea. So I'll let you check that the following vector, let's see. So x1, y2, minus x2, y1, and then minus x0, y2, plus x2, y0, and x0, y1, minus x1, y0, and then 0, 0. That vector, it's in the lattice, lambda xy. Okay, so what it means is that if you take these three numbers, and if you plug them as values of A0, A1, A2, and then there's 0, 0, 0, 0, then you get 0. Okay, same for x and same for y. Okay, very good. So what? Then, so using that kind of argument, so using, let's say, a combinatorial argument, so it's a purely algebraic thing, we can exhibit many of such vectors, which are linearly independent. We can exhibit n dn minus 2 vectors in our lattice lambda xy, which are linearly independent. And what's very important for the argument is that these vectors, they have a norm which is rather small, and whose norms are at most twice the norm of x times the norm of y. Okay, and if we have, so I didn't tell this, but of course the rank of our lattice, lambda xy, it's exactly that number, capital N dn minus 2. So we have a maximal family of linearly independent vectors in our lattice. So this implies bounds, so it implies that the successive minima of lambda xy are all less and less than d to the 2 over n plus 1 minus d. Okay, so that's just by definition of the successive minima, because the successive minima are the least vectors which satisfy such properties. A property like that, right? And so why is that important? Because when we want to count lattice points, the successive minima of the lattice, they're basically the only thing in which we are interested in, right? Because if we know the size of the successive minima of the lattice, then we can simply count the lattice points just using some very classical geometry of numbers argument. Okay. The shortest, so I guess for most lattices, the shortest.
I would expect that for a typical one, it would be all the same size.
Yeah.
It's just,
Yeah.
X, norm x times y to the d divided by the big n. Much smaller. That's part. Like the Poonen restriction that n is d plus 2 comes from. Yeah.
You need to wait a bit more.
I'll ask them.
It's coming, it's coming, it's coming. Yes, so then what? So since we know the size of the successive minima, just a geometry of numbers argument. Gives that our sum over v, so fv in z primitive and gn, which are in lambda xy, and whose Euclidean norm is almost a, then that thing is exactly some positive constant, cdn. Then there is a power of a, which is the rank of the lattice, like that, and below there's the discriminant of lambda xy times some error term, which is the maximum size that, I mean the size of the largest successive minima, which is bounded by this, by what we did before, over A. Okay, so that's for some CDN positive. Okay, very good. And so we have a good expression for that term. So let me, yeah, I guess it's going to be useful to, I'm going to call this the sum over xy in omega dn of b. Okay, that's just a definition, because it's going to show up again after. And I've left apart the diagonal term here. And so the diagonal term is, of course, easier. So I dealt with it in some of my earlier work. So what should it look like? So let's see. So we are summing over all hypersurfaces of height at most A, the number of rational points of height at most B. So if you think of this in terms of Manin's conjecture, then generically there should be no accumulating subvarieties. So that should be simply B times log of B to the rank of the Picard group minus 1. And generically, the rank of the Picard group should be equal to 1. So what we expect here is a power 1 for B. And we're summing over, sorry, we have a lattice condition, which is this time a rank, the rank of the lattice is n minus 1. So we expect a to the n dn minus 1 times some other constant. And that's what happens. So that's if A is at least B to the 1 over n plus 1 minus D. And here, I didn't say it, but of course, I want A to be at least B to the 2 over n plus 1 minus D. Okay, so let's sum up what we've done so far. So if I divide by the cardinality of VBN of A, the sum of the global counting function squared, so we've proved that it's some number, let's say k dn. So that thing has size 1 over A to the capital N dn. And here we had capital A to the capital N dn minus 2. So we have a power 2 for A, which ends up here. And then there is the sum over x and y in what I called omega dn b of 1 over the determinant of lambda xy times the other terms. So 1 plus big O of b to the 2 over n plus 1 minus d divided by A. Plus the diagonal term, which is big O of b over A. All right, so that's what we've done so far. Okay, so that was for the first term. So I'm not going to spend 20 minutes on each of the 3 terms, but in 5 minutes maybe. So what happens for the second term? So the mixed global localized term. Okay, so one thing that Will said, I think, is that the localized counting function, if you remember its expression, there was simply, basically, so there were many conditions, and the 2 important conditions were the ones dealing with alpha and W. So the condition over alpha is just some space condition, and the condition over W was simply a v of x equals 0 modulo W. Okay, so in mv of b alpha W, we have that condition. So actually, that thing, that localized counting function, it's designed in such a way that we can still apply geometry of numbers, because that thing, it's still linear in the coefficients. Okay? So we can keep on using our geometry of numbers arguments. And I guess it's the whole point of that expression for the localized counting function. Okay, so what do we get? So this time, so I'm not going to do everything again. I'm just going to tell you what happens in the end. So we get a main term, which looks like that. Yeah, it's like. So we do everything exactly the same way, and we end up with our same constant here, divided by a squared again, our sum over x and y in the set omega dn of b of 1 over the same thing, the determinant of lambda xy, times something which is a bit different. Let's say 1 plus big O of the minimum of 1 and something which I will call error of x and y. Okay, so when we do the geometry of numbers, we get almost the same main term here. So 1 over the determinant of the lattice, times something which is an error, which is due to the fact that one factor is the localized counting function and not the global one, basically. Okay, so where error of x and y is small whenever x and y are far away from each other. For the Archimedean topology and periodically for any prime dividing capital W. Okay, so of course I'm hiding many pages of dedicated estimations, but in the end, morally, that's what we get. Okay, so we get almost the main term with a small error, and the error is nice when x and y are far away from each other, both for the real topology and periodically for any prime dividing W. And here I mean in terms of alpha, of course. Okay. Okay, so now there's two cases. So either x and y are far away from each other, both for the real topology and periodically for any prime dividing w. And then we're good because we get exactly the same term here and there. And if it's not the case, then we are in some kind of trouble. But of course, it's if you take randomly two vectors x and y in R to the n+1, then the probability that they are in some cone very close to each other in terms of alpha, if alpha gets large, then the probability gets small. Okay, so that's the idea, and periodically, then it's the same idea. Okay, so
Do you mean times dividing W? Should it be times not dividing W? Because the bigger W it is, the one would be periodically far.
yeah, sure. Can you see that? I cannot, but sorry. Yeah, thanks. Yeah, I'm going to display some W, and your comment is going to make sense. So let's see. Yeah, so if alpha is large enough, and capital W divisible enough, then there are few xy which are bad. Okay, so that's what Will meant. So here is the fact. If we take alpha equals log b and W equals, it's going to be something technical, but at least you will know that we have a value of capital W which works. So we are looking at the product over the primes, P, bounded by log B over log B. To the some power log B over log P. That's the seeding part, plus 1. Okay, so that's, I just wanted to display a value of the W. So we see that as B gets large, then W gets more and more divisible, and there's less and less x and y for which we are in trouble. That's the idea. Okay, so I'm going to call this star, and now you can forget about it. Okay, so now, okay, and with this, what do we get? We get that if we look at the sum over V in VDN of A of the global counting function times the localized one, then we get exactly the same main term, and I should give a name to it. So let me call this, let's say that this is M of A and B. Okay. Okay, so now I get the same thing, m of a and b, times the same error as we had before, b to the 2 times n over n plus 1 minus d over a, plus something which comes from alpha and w, some small power of log b. We have a small power of log b saving. I think it's 1 over 2n, plus big O of the diagonal term, so a, b over a, sorry. Okay. And for the third term, let me just tell you that it's the same, more or less. Same story. So that's the pure localized. Okay, so now let's put everything together. So in the end, we get that the variance V of AB alpha W is so M, the main term of A and B, times, so I'm putting all the terms together. So for the first term we have +1, then we have -2, which comes from the mixed term, and then a +1 again, which comes from the pure localized term, plus the error, b to the 2 over n plus 1 minus d over a, plus 1 over log b to the 1 over 2n, okay, plus big O of b over a. And now the magic happens. Beautiful. Okay, so what do we get? We get 0 here, so we get just m of a and b times this plus that. Okay, so here I'm missing 1. Okay, and another fact which I don't want to prove. So if the sum over xy in our set, which appears in the main term there, of 1 over the discriminant of lambda xy. And this is less and less than b squared. Okay, and it's actually the right size. Okay, so let me not say anything about that. So in the end, we obtain v of a, b, alpha w is less and less than, so in here we had 1 over a squared times b squared, so b squared over a squared times b to the 2 over n plus 1 minus d over a plus 1 over log b to the 1 over 2n plus b over a. So if I factor b squared over a squared, I get a over b. Okay, so thanks for being so patient. We're almost there. So now we can finally state a completely explicit version of proposition 1. oh, it's there. Yeah. Yes. Okay, so if you remember from proposition 3, we needed the variance to be smaller than b squared over a squared times eta cubed. Okay, so in the end we want each of these 3 terms to be less and less than eta cubed. We want b over 2 over n plus 1 minus z over a over b, and 1 over log b to the 1 over 2n to be less and less than eta cubed. Okay, so for this one, it's going to be always fine because b is going to be a function of a, any function of a which tends to infinity as a tends to infinity. So it's going to be fine. But for these two, then we get some condition. Okay, so in particular, we need b over 2 to the n plus 1 minus d divided by eta cubed. We want it to be at most a, and we want a to be at most eta cubed times b. Okay, so now I can state a completely explicit and accurate version of proposition 1. So let me maybe look at my notes. So let eta 0, 1, let b be large enough in terms of eta and such that this, let me call this star star, and also let alpha and w satisfying star. Then, so what do we have? So we have alpha and w, which are functions of b. B can be any function of a which satisfies this. Eta is fixed. And then we take the lim sup over a tending to infinity. And what the proof of proposition 1 showed at the beginning was that this is at most eta, which is good enough for what we want. Okay, so if we look at these conditions, so for alpha and w, they're all good. There's no condition. But for b, so what happens here? So if, let's say that we start with n equals d, then here we have b squared divided by something, needs to be bounded by b. Okay, so we are in big trouble. Okay, so if n equals d, this completely fails. If n is equal to d plus 1, then we get b divided by something which is small. We need it to be at most something which is small times b again. So it fails, but from almost nothing. Okay. That fails. But if n is at least d plus 2, then here we have a lot of room. So if n is equal to d plus 2, then here we get b to the 2/3, and here we get just b. So we can just take b equals a over eta cubed, and we're good, for instance. Okay, so it's an easy success. I don't know if I should say easy, but okay. So now I need to add a condition in proposition 1. So we want d at least 2 and n at least d plus 2. Because if we don't have that, then there's no choice, there's no possible choice of d, right? Okay, so that's the reason why we need n to be at least d plus 2. Yeah, I guess I should stop. I hope it wasn't too technical, but I made the presentation so that, I mean, I wanted to give as many, as many details as possible. I wanted to give as few details as possible in order to make sure that I can still get to this condition, in order to show you why we need that, but I hope it wasn't too painful. In French, we say, on ne fait pas d'omelette sans casser des œufs. We don't make omelets without breaking eggs. I hope I've not broken too many eggs this morning. Yeah, I'll stop here. Thanks.
So please, questions. Wait. Sorry. That's very cool.
How high a moment can you get?
Sorry?
How high a moment can you get? Like, you got the second moment.
Yeah.
Can you get a fourth moment, for example?
Well, I guess that would worsen a bit that thing here, so we would end up with a 4 here.
I'm just curious.
Yeah, so if we try to do it, then we're going to end up with a b to the 4 divided by n plus 1 minus d. So we're going to maybe, if I'm not mistaken, we're going to need n at least d plus 4 or something. But that's not going to bring anything new for the proof.
Not for proposition 1, I'm just curious.
Yeah. So I guess, so if n is large enough in terms of d, then I guess we can deal with all the moments, basically. Yeah.
Other questions?
Concerning n equals d plus 1, the method does not work, or you think it's a problem?
Let's say that what I've shown you this morning does not work, but we are not so pessimistic. I mean,
How do you have room?
Yeah, there's a bit of room in the way we look at the successive minima. So if we win just a bit there, then we're good. But what's clear is that n equals d is completely hopeless. So that's the next hard case.
Okay.
But we are working on this, and yeah, we think it's going to end up fine.
And one more question. What happened with proposition 2?
Yes?
Any more questions, please?
Have you also thought about smaller families of forms, like diagonal maybe, or something like that?
So if we look, as Will said, Bruden and Dietmann, they have dealt with the diagonal. But of course, with diagonal, they don't have any way to use that combinatorial argument that I explained. So that's why they end up with not the condition n at least d plus 2, but they need n at least d plus 2d, which is what I had at the beginning when I said if we count in the most elementary way, we get this. Okay, so they need n at least 3d, but they have much less variables, so it's a harder problem.
But you could also probably use other techniques like the circle method, right, for the like pure global sum. That,
I mean, it's a linear problem, so it's just.
yeah.
I mean, it makes sense to just use geometry of numbers, but But yeah, I guess we could deal with some smaller families, like if we have all the degree d, I mean all the x0 to the d, x1 to the d, so diagonal monomials, and also the monomials for which we have exactly two variables. So x0 to the d minus 1 x1, okay, exactly two variables, not more. Then I guess that would be enough for the combinatorial argument to work. And so we would need actually much less variables than the entire n plus d choose d variables. Okay, I don't think we need an exponential number of coefficients. Okay, we just need some polynomial, but yeah. But just diagonal doesn't work.
Okay, if there are no more questions, let's thank both speakers for the excellent talks.